So thank you. It's a true pleasure to be here to speak at a Research Methods Festival. In the United States, we don't have Research Methods Festivals because research methods are not fun. They're not something you would have a festival for. I was going to talk about some political science things and polling and public opinion, but I thought about it and I thought it's not really going to work here. There's not really much interesting going on politically in the United Kingdom right now that I could think of. So it seemed like it's really things are pretty quiet politically here. So instead, I'll talk about some other things. There's a little political science at the very end. So I'll start with this. I can't actually click and show you the video. This is said to be the second most popular TED Talk of all time. Does body language shape who you are? And this researcher claimed that if you hold your body in a certain way, then good things can happen to you, and good things can happen to your hormones. I'll skip the details, just go to the study and the replication. That's right, you reacted appropriately. Now, I want to tell you a little trick, which is how to think about this. Think if you see this, and there is some discussion in the replication paper, but what happened, how come this study didn't replicate? Like maybe the replication was done a little differently. You know, you can't really do everything identically in a replication. Maybe the replicators were missing something. Maybe there was some special sauce in the original that didn't, you know, all sorts of possibilities. So I have a way, and I'm going to tell you this, like how to understand this. It's a trick, okay? And the trick is that you do a mirror reflection of this, and you consider the study on the right as coming first, and the study on the left as coming second. In that case, what we have is a controlled pre-registered study consistent with no effect, followed by a small sample study that was completely uncontrolled, where the researchers were allowed to look for anything, and they happened to find something that was statistically significant. Now, from that perspective, this seems very consistent with null effect, or a signal that's much smaller than noise. Now, I wrote about this in the popular press. I called it the latest example of scientific overreach, which I would no longer say that anymore because, of course, there have been later examples of scientific overreach since then. But at the time I wrote it, I think it was correct. I posted this on the blog, and a commenter wrote, "Oh, and while we're on the subject of sloppy reporting, have a look at 10.111. Well, I don't know the code, but I can cut and paste into the browser window just like you can." So I went through and I found this paper about the pervasiveness and persistence of the elderly stereotype by some authors who we've encountered in other contexts. Americans stereotype elderly people as warm and incompetent, blah, 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 blah. Then there are the results. I don't want you to read, actually, like, I find reading such a paragraph as unpleasant as you do. And I actually don't think this is a good way to summarize your results. I think that if you have a lot of results, you should summarize them in a graph rather than sort of walking through a garden and picking fruit and presenting them like that. But if you're used to reading things like this, you'll notice that you're supposed to focus on the t-statistic, which is this one's 5.03, and this is 11.14. Anything more than 2 is good news. These are big numbers. So someone said I should look at them, so I thought I'd better recalculate these. Well, here are the data, the differences. You have to actually figure out the sample sizes, but you can kind of deduce that from the degrees of freedom, and you get that the t-statistic is really 1.79 and 3.34. Not this. So I was like, what do you do? Like, it looks like if you square 3.34, do you get 11? No, it's not that. Like, I'm not sure what went wrong. Now, what the point of this here, okay, there's 3 things that went wrong in this study, or at least 3. One, obviously, is just a crude miscalculation or misreporting. The second is the approach in which you look at a lot of things and then pull out statistical significance and jump on it. The third thing is that the underlying theory is I'm going to say the underlying theory is flexible. That's not necessarily bad. Like a theory can be flexible and useful. But the measurements taken in this experiment were not really so closely connected to the theory. They were somewhat generic measurements. There are all sorts of interactions that they could have studied. Now, these aren't three unrelated things. They kind of go together. And this relates to what I consider a very blurry boundary between research incompetence, out-and-out cheating, and all sorts of things in between, like sort of cutting corners, not quite cheating, right? Like, you know. And I think the common thread is you have researchers who believe that they know the answer. And they think of statistics as a way to prove what they already know, or as a set of hoops that they have to jump through, sort of like a bunch of paperwork. So if you see this, like, how is it that someone could get this number, like that's supposed to be 5.03 to get 1.79? Well, if you don't really care what the number is, then you can make mistakes like this. Right? Now, it's not just about silly psychology studies. This goes on in serious research too. Here, that wasn't a joke. I really mean it goes on in serious research too, not just silly psychology. I don't mean that all psychology is silly. I'm saying it's not. Let's go on. Let's continue the festival. This was a study that was done in Jamaica. 130. There's an experiment involving 130 children. They were 4-year-old children, and half of them were given, and the mothers were given special coaching, like a year's worth of training on how to be a good mother. I don't remember exactly what it was, but it's early childhood intervention. The other kids didn't get it. They just got like the usual pamphlets and good wishes and so forth. They followed these kids up 20 years later and looked at how much money they were making. And they found it was a randomized experiment, and we re-interviewed the studies 20 years later. Stimulation, which was the treatment, increased the average earnings of participants by 42%. Earnings is econ jargon for how much money you make. It's the economists refer to that as earnings. And this was, I don't believe this, 42%. Now, it's not that I don't believe it because I think that they miscalculated their p-value and they're off by a factor of 8 or whatever. It's nothing that crude. I don't believe this. Well, let's say this. This was 42%. So is this number statistically significant? Do you all know? Yes or no? We don't know. That's the wrong answer. 3 answers. Yes, no, or we don't know. It's not we don't know. So door number 1 or door number 2, which is it significant or not? Yes, because they followed the rules. It was published. You're not allowed to present a non-significant result without saying it. If they wanted to say, in this data set, stimulation increased the average earnings by 42%, but it wasn't significant, you'd have to say that. If you put this in your abstract, it has to be significant. I mean, that's just the rules, okay? You got to do that. So there's a 95% confidence interval, which is something like from 0 to 84%, or something like that, right? Or maybe 2 to 82%. Yeah. But, well, I think that 2% is more likely than 82%. That's sort of one way of saying it. I have some prior information that it's not that easy to increase the average earnings of people by 42%. Another way of saying it is we have something called the statistical significance filter, which is if the standard error here was 20%, then to be statistically significant, the estimate had to be at least 40%. So the small effects don't get discovered, or I don't want to say that, small effects don't get reported. So this is a biased estimate. Then there were actually some issues. So like it was significant, so that sort of should count for something, although there were some data issues. They actually had 4 treatments, not 2. They compared the other 2 treatments, and they didn't seem to matter, so they pooled. And then there were actually a lot of kids who left the country, and they made more money than the ones, on average, than the ones who didn't leave the country. And the ones who got the treatment were more likely to leave the country. So like, what do you do with that? Well, this is straight intent to treat analysis. The cleanest thing is you just put everybody together, but then if they're really saying, well, stimulation increased, the motivation to send your kid to another country, it seems like it's a little bit different than what they want. But really, I can't do much with that number except say it's too high. I can't do much with the statistical significance except to say that I think these people are very competent researchers. And if you're a competent researcher and you spend 25 years in a study, damn straight you're going to get statistical significance out of that. That would be, unless you want to make the point that early childhood intervention doesn't work, in which case you can say that. But I don't think they wanted to do that. You don't want to, and I say this to a room full of people. I feel like it's a safe bet that just about everyone in a room at a research methods festival supports early childhood intervention. I think all of you probably feel there should be more help out for poor parents. I think that too. So it seems like it should be positive. But that's sort of another issue, is if you already know it's positive, what's the point of doing this study? It's to build political will, maybe? So, well, I know this is going to work, but now this has convinced me. It's a little different, like the model in which you're trying to not reject a false hypothesis. It's not really what's happening here. The theories that we have are not, the framework that we use for statistics isn't really applicable here. And I think when you use the wrong framework, you do all sorts of things that don't quite make sense in that context. I have another example. This is another one where I'm sort of going to be a bad guy because it was a study saying that pollution is bad for you, and I'm going to say that, I'm not going to say pollution is good for you, but I'm going to say that the study provides no evidence. There was a natural experiment in China for many years that north of the Huai River, it's cold as you go north because China's in the northern hemisphere, and north of the river they were giving people free indoor coal heating, which sounds pretty nice because it's warm, but on the other hand, indoor coal heating might be bad because you're breathing in that coal dust. So what these people did this analysis. Each circle is a town or a city, or it's a location in China. And they're plotting the life expectancy as a function of degrees north of the boundary. And they fit a little 5th degree polynomial. You're supposed to laugh at that one, actually. They fit a 5th degree polynomial. Yep, okay. With a discontinuity. So the model is that life expectancy is a continuous function of degrees north of the river, but then there's a discontinuity. In this case, the discontinuity is estimated at -5 years. And that means that being north of the river reduces your life expectancy by 5 years after controlling for this. Therefore, and it was statistically significant. And so then they wrote a paper with a title. It was something said something like 2.5 billion life years lost or something like that. I think it was 500 million people times 5 years, so forth. Now, this is a bad analysis. And to me, what's most striking about this is that not that they did a bad analysis, but that they included this graph in their paper. So they didn't realize that this looked bad, and the journal editors didn't either, right? So, and that's a little different. Like the earlier examples I showed you, it's sort of like the mistakes are kind of hidden. Like if you know what to look at, like if you ever see a p-value, you should get worried that there was selection bias. But here it's like this is super obvious. This model makes no sense. It's actually, there's no reason to think that there's a fifth-degree polynomial relationship between degrees north of the river. Also, if you actually start staring at this, like, if you look at where that jump comes from, the reason why that red line is negative here, this jump is negative because this is sloping up so fast. But this is sloping up so fast only because the curve has to go up to reach there and then go down here, and it has to go down and then go up. So it's really being dragged around. You know, the dog is being wagged by the tail, as the saying goes. Now, if you start staring at this, you notice other problems, like the life expectancy in this city was 92. But, well, 92 doesn't sound so, it sounds pretty good, but actually if they only hadn't had the indoor coal heating, it would have been 97, you see. No, I don't think the life expectancy is 92 anywhere. I think there's some problem with the data. So these people were subject to an ideology. And the ideology was that if you do this thing called a regression discontinuity analysis, which many of you haven't heard of, but it's sort of the econ equivalent of saying, I did it in NOVA or whatever. It's like what you're supposed to do, right? Then if you do that, everything's OK. And if you're statistically significant. So I want to tell you a little story of how this happened, because I think this gives some insight. How could this possibly be right? I mean, it just doesn't make sense. There's no scientific reason to think of there being a fifth-degree polynomial. In fact, if you want to step back a moment, there's no scientific reason to think that degrees north of the river is much of a predictor of your life expectancy. The only reason they're using degrees north of the river is that one thing's happening north of the river and one thing's happening south, which is fine, but that has nothing to do with how far north you are. I mean, not to mention, if you're looking at raw life expectancy, you might want to look at things like smoking rates, because that's always there's a rule in public health that for any cause of death X, the interaction of X with smoking has a bigger effect than X alone. You always have to include smoking. So what went wrong? So it goes like this. You have this discontinuity, and you need to, the idea is that you could look at the data locally, and if you see a big jump right at 0, that indicates that something must be happening. Well, so the natural thing would be you fit a linear model, linear regression, and have a jump. Now, if you fit a linear regression, you don't get any statistically significant jump. But then you'd say, well, actually, you might have heard this because it's said, like it's in my book with Jennifer Hill, we say if you're running a regression doing causal inference, control for as many pre-treatment variables as possible. So let's control for a quadratic term, and a cubic term, and a fourth-degree term, and a fifth-degree term. That's going to be safer. We always say this. This is the advice we give. You control for more things. You only care about the causal thing. So why shouldn't you control for too many things in a regression? Well, the usual thing you're told is that you shouldn't control for too many things because if you do, it increases your standard error because you're throwing noise in. But obviously, the standard error wasn't too high here because it's statistically significant. So therefore, it was retroactively OK, and that's the reasoning. Now, that's actually mistaken. It turns out even at a purely classical statistical level, it turns out that throwing in these higher degree polynomials, even if there's no effect, it turns out the probability is much more than 5%, that your 95% interval will exclude 0. Just sort of counterintuitive, because it seems like if you just throw in noise, it shouldn't mess up your p-value. But actually, you're not throwing in noise. You're conditioning on powers of this x variable, which is not noise. It's correlated with all sorts of things. So it's sort of a bunch of complicated steps, and I don't really mean to make you have to start thinking too hard at the end of the conference. But I wanted to emphasize that there's an ideology that goes with this, and along with the ideology is a set of logical steps, and everything sort of fits together. And that's the way ideology is. I heard that here in the UK. I've heard that Marxism remains popular, and that's like, there's a whole story about that. Like, everything sort of fits. In the United States, we have the, what's it called, the free market capitalism ideology, and it's sort of the same thing. It's like another version of Marxism where, like, it's not merely, an ideology is not merely that you have a strong belief. An ideology is a strong belief tied to a logical system. So you can explain things. It's not, these things are not empty. And in this case, the ideology, as false ideologies are, it has holes in it. There are certain things that are not true. In this case, there are certain assumptions about what these things being significant. Okay, so let me just, this thing was published. It was reported in the New York Times, and I give this headline just to point out that it says research, pollution leads to a drop in lifespan, research finds, not research claims, right? So it's just assumed to be correct. It was published in a prestigious journal, and that was the story, okay? But it was based on this. And it's, in a way, it's a little scary, but that they didn't realize how foolish this was. But again, their ideology said it doesn't matter how foolish it is, right? Because this is stronger, the logic is stronger than direct evidence. So now that I've given, how long am I supposed to speak till, by the way?
We're flexible, maybe 15 minutes, but something like that.
Okay. So I've told you about some crimes now. I'll tell you another story. So somebody sent me this in the mail, and I think this sounds like the kind of thing that I might laugh at, but actually I kind of like it. So influence of Valentine's Day and Halloween and birth timing. So they had a graph here. So here isn't that, you see? And look, isn't that cute? I don't know if they do Halloween here, if it's just an American holiday, but you've heard about it, right? So more babies are born on Valentine's Day, and they compared it to the week before and the week after, and it seems, and this was statistically significant. You see the star there. Actually, interestingly enough, more natural births on Valentine's Day as well as more induced births, which you might be surprised, because it's not surprising that if you're going to induce the birth, you do it on Valentine's Day rather than on the day before Valentine's Day. It might be Friday the 13th, so which do you pick? Well, I don't know, might as well pick Valentine's Day. So it's not, but somehow it seems funny that there are more natural births on Valentine's Day too. We'll get back to that. Here's Halloween, and there are fewer births on Halloween. It's a scary time to be born there, apparently. So I saw this, and I was a little worried in that, you worry about, yeah, it's statistically significant, but there's a lot of days in the year. And Halloween and Valentine's, they're not the most important days in the year either. I don't know exactly how the researchers picked those 2 days. Of all the days to pick, I wanted to see all 366 days. So here they are. Somebody made this graph. These are all the births. This is a data set from in the United States. It was from 1968 to 1988, just number of babies born each day. And we took that, and here you see, well, ignore the curves. That's sort of silly. The person fits a smooth curve. But fewer people born on New Year's, and, well, maybe more people born Valentine's. It's not completely clear. Fewer on February 29th, even after you multiply it by 4, maybe. It's not completely clear. Fewer on July 4th. It's a holiday we celebrate in the United States. You haven't heard about here. Here's Halloween again, and then this of Christmas I've heard is big in here, so you've heard about that. Then, of course, there are more people born on December 30th. Well, the baby has to come out sometime, right? So it has to sort of work out there. If you look at this, there's some funny zigginess about this. There's about 52 periods in this graph. And that's because we don't have exactly 28 years of data. So there's some confounding of day of week with date of year. And of course, you've probably heard that fewer people born on the weekend. So we want to better try to do some further analysis here. The raw data don't. I'm a little worried. If you look at a particular day in a 20-year period, that there could be some confounding. So we better study that. So I asked people to do some more. Someone made this graph for me, which is sort of cute. I hate it. I hate this graph. Well, it's really good because I can compare the 21st of every month. I really wanted to do that. So, graphs are comparisons. So you have to sort of think about a graph, think about what comparisons a graph facilitates, right? It's like that's what a graph is. A graph is like, to continue with the Valentines theme, a graph is a kind of a matchmaker, right? Like a graph is essentially you have a lot of information, and a graph is connecting those information so you can make it visually. So then you really want to say, do you want these numbers to be all the same line? Well, maybe not. This graph does tell me that more people were born in the summer, but I already could better see that with the time series. How about this? This was nice. My colleague Aki did this. We put this on the cover of our book, actually. It's a time series decomposition. So we have the data from 1968 to 1988. We decomposed it into a slow trend. There are more babies born, then fewer babies born, then more babies born. This fast non-periodic trend, which is just there are times when it's more or less popular to have a baby. I mean, things happen. Short-term economic crisis. Everyone knows, when people are richer, they're more likely to have a baby. There's news, maybe the queen. You have a queen here, right? It's like queen has another kid, and then that's a big news. Whatever is happening during that time. In the United States, it wouldn't be the queen, it would be like a TV star or something like that. Same idea. Now we have the day of the week, and indeed fewer people born on the weekends. We broke it up by year, and you see that the day of the week effect increases over the years, which makes sense because there are more induced births, more C-sections during this period. Then we have time of year, so more babies are born during the summer, which means more babies are being produced in the winter. Then we have these day of year effects. So this is pretty cool. We did not specify these dates. What we did is we said, estimate 366 things and see what happens. And we see fewer. Valentine's Day picks up, so this is really nice. Like you look at the data and you decompose, and it pops right up in a way that really seems plausible. Here's Leap Day, April 1st, less popular day to have a baby. Independence Day. Labor Day in our country is not on May 1st. It takes a whole week, so this is spread out over a week. Here's Halloween, here's Thanksgiving, and then here's Christmas. Sorry, okay, there's that. We give you more like statistics fun, okay? So then recently someone sent us new data. Was for more recent years. I can't remember. Maybe it was like 2000 to 2014, I think. So we refit the model and the new data. So, well, of course, we see a different trend. I mean, the long-term trend is different. There's a little bit of a baby boom. The day of the week effects now are not changing much from year to year. But that makes sense, because since 2000, it's been stable, the percentage of births that are induced or C-section in the United States. Now we have the seasonal effect, it seems a little lower than before, and then finally we have these special day effects again, and these are larger than they used to be, which makes sense, because compared to the 1968 to 1988, there's more choice in when to have your baby, because more. And now look, amazingly enough, in Christmas, like half, the number of babies born Christmas is half of the number, and so that, roughly speaking, it suggests that half the babies were sent somewhere else to have a baby another time. Now, as I said, this can affect natural births too, because you have the birth, it's going to be scheduled, and it's not scheduled on Christmas, it's scheduled on December 24th. But then you have a natural birth on December 23rd, so there's fine. But you don't have a natural birth on Christmas because it was scheduled on the 24th. I mean, for example. So you can sort of have a bunch of things like that. So it's an interesting selection problem that it can show up. Whether a birth is natural or whether it's induced is itself an outcome of the process. It's not a property of the baby. It depends on the decision-making process. Now, I can even stare at this more, and like, there's problems with this model, and I'm going to give you an example. These are supposed to be special day effects, which this makes sense for your New Year's, Valentine's, Leap Day. Look at this. According to, this is September 11th, which is a day where people don't want to have a baby also. 2 weeks, during these 2 weeks, the special day effect is positive. Now that just can't be, right? You can't have too many babies for 2 straight weeks, right? So really, this belongs in the seasonal effect. But because you're fitting this additive model, it put it in the wrong place. Now we should be able to fix this. There's ways of fixing this in the model. You basically constrain it to say it has to average to 0 locally. This is the baby has to come out sometime principle. That's not in the model. And since it's not in the model can screw up. But this is how we take our model seriously and we interrogate it in this way. And you can do more. We blew up that last graph because somebody asked us about the 13th, and the 13th is less popular every month. We hadn't noticed, even here, you see. I mean, that just popped out, right? Like, isn't that funny? So it was all there for us to find once we looked for it. Now, in statistics, we call this, there's a saying, the blessing of dimensionality, which is that if you study more questions, you can learn more. In mathematics, I don't know how many of you took any sort of, advanced math in college or university, whatever they call it here, but there's a saying in math that if you can't solve a problem, the way to solve it is embed it in a harder problem. And that's really true. Like things like Fermat's last theorem, the way they solve these problems is like instead of making a statement about numbers, they'll make it a statement about polynomials and solve that. Like it turns out there are many mathematical problems that are actually easier to solve if you embed them in larger problems. There's a similar thing in statistics. So we learned a lot more about Valentine's Day by studying all 366 days. Right, because you might think if you care about Valentine's Day, just focus like a laser beam on that week. But no, you can learn more this way. Okay? So, and then I want you to consider the alternative. So this is an example. This was a study. They did a survey and they asked some women when was their last day of their menstrual period. And who do you support for president? Barack Obama or Mitt Romney. And they found that women in a certain time of the month were more likely to support Barack Obama, which was sort of consistent with the idea that Obama was like the girly candidate. During that time of the month, you're more girly. So actually, that's not quite what they found. They found an interaction between the time of the month, your time of the month, and whether you were married or not. So the single women during that time of the month were more likely to support Obama, but the married women were more likely to support Romney then, which makes sense because Obama is Romney's like a married guy, like a real beefy guy, a married woman can really appreciate. Obama's he's dangerous. He's an immigrant, all these things. I say this in the United States and people don't laugh. They're like, yeah, right, so actually it wasn't that. It was not whether they're married or not. I'm sorry. It was whether they're in a relationship or not. That was the variable. So they found this statistically significant pattern and told a story. And it's possible to tell a story. It's possible that you can have data that really go in all directions, but you can use it to tell a very strong story, right? Even, you might not believe it yourself, okay? Now, I didn't mean to bring up Tony Blair at this point, but this can happen to any of us, that we overinterpret our data and use it to blow up entire countries, right? But let's try to think, how can we think about this quantitatively? Now, the study had no chance of succeeding. The reason why it had no chance of succeeding, I will actually have to explain. I'll have to get back to this. I'll get back to this example. But the study had no chance of succeeding because the underlying effect, if any, is quite small. and the noise level is quite high. I have studied public opinion. I studied the 2012 election, and during the last couple of months of the 2012 election, fewer than 2% of people changed their opinions. Okay. So that's total change of opinion. Out of that, what amount of that 2% is coming because it's a different time of the month for you? It's got to be pretty small. Okay. They had an estimated effect of 20%. 20 percentage points, which means the standard error was about 10 percentage points. You can't do it. You cannot do a study where the true effect size is less than 2 percentage points and the standard error is 10 percentage points. We can do it. It's called a low-power study. There's a small chance you'll get statistical significance. If you get statistical significance, you lost because you became very confident in something that is just noise. And I'll get back to that in a bit. So the study had no choice, actually had no chance to succeed. And I'm going to get back to it, but I don't know if I have time. How much time do I have now? Like 5 minutes left?
It depends how much time we want to have the question.
You decide. Look, I don't know. I'm just speaking. You tell me how much more longer I should speak.
Try not to go past 3 p.m. on that.
Oh, okay, sure. Okay. Okay, that's 10 a.m. my time, right? Okay. I'm still waking up here. Okay. There was a study that was done, so I'll give you a little background. It was a psychology study. Students were asked to perform some meaningless task, at the end of which they were told, hey, go down the hall and pick up your printout. Now, it turned out that the entire purpose of the study was to see how long it took them to walk down the hall to pick up their printout. And half the students were given a regular task with a bunch of words. The other half were given the same task, but in the words were thrown in a few elderly-related words, such as bingo and Florida and Brexit and tenured professor and things like that. And this is what they found, that when, I was like, I know I can get Tony Blair into this one, but how am I going to work Brexit in? And it just came to me just then, because I wanted to do it. And I was like, I'm going to wait till the right time. It'll come. And it did. It was perfect. It was perfect. It just came to me while I was doing it. I threw it in. It was like, just for you. Yeah, so the people primed with the elderly condition took longer, a lot longer to walk. It was pretty striking and so consistent, too. So this was published, and it's been cited, I think, 3,600 times. Daniel Kahneman, noted psychology researcher, wrote, when I describe priming studies such as that to audiences, the reaction is often disbelief. The idea you should focus on, however, is that disbelief is not an option. The results are not made up, nor are they statistical flukes. You have to have no choice. No choice. He's serious. He looks happy, but he's serious. Okay, well, some people decided to replicate this study. Now, despite the font here, this was actually done not in the 1970s, but fairly recently. Elderly wage rulers, and they replicated the study. Here it is. Okay, well, there's a difference. It's not statistically significant, but there's a difference, right? So you could call it a successful replication. Although, actually, wait, the people with the elderly words went faster, but it's not statistically significant, so don't worry about it. So here's the Kahneman quote. Then anyway, Wagemakers et al. Wrote, after a long... I know, isn't that great? Isn't that just the greatest quote? I love that. It is. It does remain an option. Now, I have another quote. So this is from Alan Turing from 1950. I assume the reader is familiar with the idea of extrasensory perception, blah, 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 blah. These disturbing phenomena seem to deny all our usual scientific ideas, how we should like to discredit them. Unfortunately, the statistical evidence, at least for telepathy, is overwhelming. Now, I was talking with Turing about this the other day, and good, you got it, yeah. No, this is the thing. I'll get back to this, but I think it's completely legitimate to believe in telepathy and all that. It's possible. I don't really know. I'm not an expert in this field. But I think we could all agree that the evidence as of 1950 was not overwhelming. Now, what's my point here? Condiment and Turing are brilliant. I mean, Condiment had made many discoveries which are more important than anything that probably any of us in this room will do in our entire lives. Turing was a genius, invented computer science, and oh yeah, he won World War II, right? Okay, but not just that, not just that these were great men, it's dead white males, as we say in the United States, but also that they were experts on information. So Turing cracked the code by quantifying the amount of information in nearly random signals. Kahneman's work, his fundamental work with Tversky in the 70s, was all about how psychologists misperceive uncertainty and variation. So what I'm saying is this is so hard. So my point is not to make fun of Kahneman and Turing, who are just brilliant and great in every respect, but rather to say that these people who are not just brilliant, but experts in this area still got it wrong. That's how hard it is. So maybe it's hard, okay? And so that suggests that we need tools here. We need rigorous tools. It's not enough to look at the data like that, okay? This is just a story about psychology papers often won't just have one statistically significant finding. They'll have 9 experiments, all of which are significant. Well, here there are 3. I just found that one. And it often, I think a lot of people feel that, well, maybe you can sort of cheat a little bit, cut some corners and get 1 significant result, but how can you get 9 statistically significant results? The chance of that is 1/20th to the 9th power. How could that happen? And I think there's an intuition. That's a wrong intuition, because when you have 9 studies, you might have 90 options in your data analysis, and those are multiplicative themselves. So indeed, you can have 20 to the 9th possibilities, amazingly enough. Okay. It doesn't mean you did 20 to the 9th different analyses, but they're possible. I will skip this funny slide. It's a cute joke, but you'll missed it. You do not get that joke today because we do not have time, because I spent that time on Tony Blair instead. It's another thing to blame Tony Blair. Yet one more thing. Back to this study. So remember I said I promised that we would try to quantify what happens with all the researchers' degrees of freedom in this study. So here are a bunch of choices that the researchers made. Now, amazingly enough, these are not choices in data analysis. These are not different ways the researcher could have analyzed the data, like different interactions, different forms of the regression, all the things that you would do in a robustness study. It's none of those. This was all just choices in the processing of the data, the things you don't even think about. There are different ways you could exclude people from the study. Like someone says, I had my last menstrual period 38 days ago. What do you do with something like that? Do you exclude that person, or do you say they're on day 38, right? They have a question about how sure are you? Do you exclude people like that or not? There are different options here. Now, we knew there are different options because we looked at other studies in the same literature, often by the same people, and they did other options. So we know that they're out there. How to assess it, how to assess relationships as. You multiply these together and you get rid of the ones that contradict each other, and you get 168 possibilities, 1 for every hour in the week. We took their data. They were very nice. They sent us their data, and we ran all 168 analyses. And these are the blue one is the one that they reported. Yeah, I don't think they ran 168 analyses. I think that they looked at the data and they were very sensible. So you see, should you exclude this person? Well, she says it's day 38, and she's voting for Romney. That doesn't even make sense. Let's exclude. Like that. You sort of do it. It's like you're walking through a garden, right? And you choose different paths. Each time it seems to make sense. You never you don't have to explicitly run the alternative analyses. You just make decisions. Now, this happens a lot in the context of medical trials. It's a well-known problem that they like to drop out people who are getting better under the control. I mean, people are getting worse under the treatment. It's obvious you can't, like, you're not supposed to do that. But people are getting better under the control. You try to figure out a way to drop them out. That's different. In medical trials, I think they're doing it on purpose because there's big money involved. Here, who knows? But you can, as I said, you can sort of quantify this issue. These are all the 168 different p-values that you could get. And this is what they actually had. They actually found, reported. This is important. I think I want to tell you this, although it's sort of quasi-technical. Do you want to hear something quasi-technical? Yeah? Okay. So I got this email from a well-known psychology researcher who I'd never met, actually. And I had mocked one of these studies I said something like, well, even if it didn't have all these flaws, it would just be telling us what a bunch of college freshmen think. And like, that's not maybe very generalizable to the population of voters or whatever. And he wrote, complaining that subjects in the experiment were not randomly sampled is what freshmen do before they take their first psychology class. That's first-year students, freshmen, they call it here. I really hope you know why that's an absurd criticism, especially of authors who never claim that their study generalized to all humans. Indeed, they only claim to generalize to all women. But from this statement, I coined the term the freshman fallacy. So the freshman fallacy is the fallacy of thinking that just because a freshman says something that it's wrong. But this is funny. This is the quasi-technical point. It's interesting. When I was a student, I was taught that if you have a randomized experiment or a survey, random sample, whatever. Well, let me just say, if you have a randomized experiment, then the people in the experiment don't have to be a random sample from the population. Because with a randomized experiment, you're comparing the treatment to the control, and they're balanced by definition if it's randomized. So you're getting a kosher estimate of the treatment effect. And indeed, like medical trials, they don't randomly sample people from the population and give them angioplasties or whatever, right? It doesn't work that way. So like, fine, okay. But that's under the assumption of a constant treatment effect. If the treatment interacts, then if you don't have a representative sample, you're getting an estimate of the treatment effect interacted with whatever sample of people you get. Now remember, we've been talking about studies where the interaction is said to be larger than the main effect. And so indeed, these studies are completely invalidated if the population is not relevant. But he didn't realize this because this is this ideology. He remembered, somebody taught him that if you have a random sample, if you have a randomized experiment, you don't need a random sample. But he was wrong. So he made the freshman fallacy. Says, I think we should be doing more with in-person studies. This is just some data, like each line is a different person, just to indicate if you can compare people to themselves, you'll have less variance. Trying to think of how to do things better. Well, why don't people do with in-person studies? I think they're worried about poisoning the well. That is, if you ask someone a question or have them do something and then do a manipulation, ask them again, you've asked the same person twice. Poisoning the well is an issue, but it's a trade-off. Yes, you don't want to poison the well, introduces some bias. On the other hand, if your variance is huge, everything's impossible anyway. So you have to worry about that. This was the example I was giving you before. That study, suppose that the true effect size is 2 percentage points. And this curve represents what you might see in the data because there's a standard error of about, in this case, I think 8 percentage points. So this is 2 standard errors. There's a certain probability that your estimate will be 2 standard errors away from 0 and statistically significant. But if it's 2 standard errors away from 0, it's going to be at least like 16 on this graph. So it's going to be at least 8 times or 9 times larger than the true effect size. It's also likely to be in the wrong direction here. But this is sort of important because people talk about power as if their goal is to get statistical significance. But this shows that if you get statistical significance, it's actually bad. I don't know what the right analogy is. Like maybe like I do a lottery, and if I win, I get to fight a bull in a bull ring. That's like not good. You don't want that. Like that's like getting statistical significance means you're sort of somewhere. It means you're sort of either here or here, but you don't know which side. So you might have the wrong direction. But either way, you're way overestimating the effect, which you don't want to do. These are a bunch of things that people have published papers on in reputable, highly reputable, respected journals and got publicity on, things that are supposed to affect how you vote, have large effects. Your monthly cycle I told you about. Oh, there's something about college students, men with fat arms being, anyway, you don't want to hear about that, but there's a study. It was supposed to be about men's upper body strength, but it was actually like they had a bunch of college students like putting tape around their arms to measure the circumference of their arms. So it was actually college students with fat arms having certain attitudes. If you flash a smiley face on the screen, it's supposed to create big changes in your attitude towards immigration, which I can't imagine because attitudes towards immigration are so rational. No, but in all seriousness, the attitudes towards immigration are ingrained and they're not going to be changed by flashing a smiley face on the screen. College football games are supposed to affect the outcome of the presidential elections. There's also a paper claiming that the 1916 presidential election, in which Woodrow Wilson won, was determined by shark attacks on the Jersey Shore. Now, what I want to say about this is that this can't all be correct. So there's a world, and it's not just social psychology, it's also sort of claims about really effective medical treatments or claims about really effective educational treatments, things that can help or hurt in different ways. That, you know, who knows like what a shark attack could do? It could have various unexpected effects. Okay. You know, the butterfly effect, right? The flapping of the butterfly here can affect a big deal somewhere else. Like if a butterfly flapping its wings can affect something, then a shark munching on some, tourists could really affect things. But the claims here are not that these can have large effects, but that they have large and consistent effects. And you can't really have all these large and consistent effects all happening at once. Like by their nature, because they're not highly correlated with each other, like they can't look consistent. I use the analogy of it's like the social world, for this to be true, the social world will be like a fish tank full of piranhas, right? Every large effect is like a piranha. You can't have like 100 piranhas in a fish tank because, they'll eat each other, right? Like you can't, it's just not sort of mathematically possible. And I think that a lot of our statistical methods are wrong. That's why it's a great conclusion to your Research Methods Festival, is that I think that the statistical methods that we've been trained on are bad. They're wrong. And one way of seeing that is if you think about things like medical research or education research, like it's incremental, right? Like a new treatment's going to be a little better than the old treatment. In fact, ethically, you're not even allowed to study a treatment that's not incremental, right? Like if I have a new medical treatment, I have to compare it to the best thing out there. I'm not allowed to compare it to a placebo, right? It's like we have this new, heart attack pill, or we'll give you a placebo. That's not cool, right? We have to compare. So if you think that like we have incremental improvements in education, in medicine, in therapy, psychotherapy, whatever it is, incremental effects are going to be small. And yet, people are using, so we can't continue to use methods that overestimate our effect sizes. It just can't work. I do think there's hope, and that the birthday example is supposed to illustrate how I think if we study many things at once, we can learn more, rather than trying to study things in isolation and try to find these big effects which really aren't there in the first place. So that's all for today.